Hi, my name is Aditya Rajajit and my registration number is URK23CS1010. In this experiment, we are working with a wine quality data set, and our goal is to identify which chemical properties actually matter when predicting wine quality. We'll be doing this without using the scikit-learn for most parts, so we really understand what's happening under, behind the scenes. So when you have a data set with many features, not all of them are useful. Some might be redundant, some might be noisy, and some might not even relate to what we are trying to predict. So feature selection and extraction helps us reduce dimensionality, which means faster training, less overfitting, and often better accuracy. So today we'll explore 14 different techniques to find the most important features in our wide data set. So let me show you the code. So first we import all our necessary libraries, pandas for data handling, numpy for calculations, matplotlib for visualizations. And we are also importing some specific functions from the scipy and sklearn. From scipy and sklearn, but only for evaluation metrics, not for building the models themselves. So in question one, we simply read the CSV file. Our dataset has 12 columns, and it has 11 chemical features like fixed acidity, volatile acidity, alcohol content, and so on, and the one target column, quality, which is a rating from 3 to 8. For question 2, we drop two columns, chlorides and free sulfur dioxide. These are specified in the experiment. I used in place is equal to true to permanently modify the data frame. Then in question 3, we identify columns with outliers using the IQR method. So let me explain how this works. For each numerical column, we calculate Q1, which is the 25th percentile, and Q3, which is the 75th percentile. So the IQR is Q3 minus Q1. Any value below Q1 minus 1.5 times IQR or above Q3 plus 1.5 times IQR is considered an outlier. So I created a temporary data frame using copy because we don't want to modify our original data yet. Then I loop through each column. I find outliers, and if a column has any outliers, I drop that entire column. So because if a feature has extreme values, it might skew our analysis. So after dropping, I display the new shape. Question 4, features. Question 4 does something similar but with variance. So features with very low variance don't change much across samples, so they're not informative. So I set a threshold of 0.5. I find columns with variance below that and drop them. Again using a temporary data frame with in place equal to true. Now we get into correlation analysis, and this is really important. Uh, Question 5 asks us to find features that have less than 0.1 correlation with our target quality. I calculate the absolute correlation between each feature and quality, and if it's below 0.1, that feature barely relates to wine quality at all. In question 6, we actually drop these low correlation features. Why keep the features that don't influence what we are trying to predict? So I create another temporary data frame and drop them, showing the size before and after. Question 7 looks at correlations between features themselves, and sometimes two features are highly correlated with each other. That's called multi-collinearity. And if correlation is above 65%, they're essentially telling us the same information. I identify all such pairs and display them. And in question 8, for each highly correlated pair, I check whether one has higher correlation with the target quality and I drop the other one. For example, if two features are 80% correlated, but one correlates with quality at zero point 0.4 and the other at zero point 0.2, I keep the 0.41. This reduces redundancy while preserving predictive power. Question 9 is straightforward. We separate our input features X and target Y. I use the exact column list given in the experiment. Question 10 uses the select k-best with chi-square test. This is a univariate feature selection method. It evaluates each feature independently and picks the top 5 based on their statistical relationship with the target. The chi-square test measures dependence between categorical variables. I have to ensure all values are non-negative for chi-square to work, so I shift any negative columns if needed. The output shows scores for each feature. Higher scores mean more important. We get our top 5 features selected automatically. Question 11 uses mutual information, which is a more sophisticated measure. It captures any kind of relationship between feature and target, not just linear ones. Mutual information tells us how much knowing a feature reduces uncertainty about the target. I calculate MI scores for all features and display them in descending order. Then I highlight the feature with the highest score. In our case, it might be alcohol or sulfates. So this is really useful because it might reveal non-linear relationships that correlation misses. And I also create a bar plot to visualize these scores. Makes it easy to see which features stand out. And then question 12. We implement PCA completely from scratch without using a scaler. So first we standardize the data. PCA is sensitive to scale, so we subtract mean and divide by standard deviation for each feature. Then we calculate the covariance matrix. This captures how features vary together. And we find eigenvalues and eigenvectors of this covariance matrix. And I use NumPy lin alg.eig for this. And eigenvalues tell us how much variance each principal component captures, and eigenvectors give us the directions. And then I sort the eigenvalues in descending order and pick the top two eigenvectors. Then I transform my data by multiplying with these eigenvectors. The result is two new features, PC1 and PC2, that are linear combinations of our original features. Then question 3 uses LDA, but here we do not use sklearn because implementing LDA from scratch is no, here we use sklearn because implementing LDA from scratch is quite complex. So LDA is different from PCA. It tries to find components that best separate different classes. So since our target quality has multiple values, LDA finds directions that maximize separation between different quality ratings. I set it to give us the first two LDA components, and yeah, I plot the results coloring points by quality. You should see some separation between different quality groups along these LDA components. Then finally, in question 14, we work with an image. I read a BMP file called zelda.bmp using a pill. Then I convert it to an NumPy array, and calculate the pixel by pixel mean. For a color image, this averages the red, green, and blue channels, giving us a grayscale representation. And I display both original image and the mean feature side by side. This demonstrates how we can extract features from images, and the mean intensity at each pixel becomes a feature that could be used for image classification later. And yeah, that's the end of this experiment. Thank you.